Engineering modern magnetic technology, from high-density storage to spintronic sensors, requires us to predict material behavior before a prototype is ever built. To achieve this, researchers must answer two mandatory questions. What specific magnetic interactions exist inside the material, and how does the magnetization move over time under those interactions? This infographic highlights the divide. On the left is the quantum scale, where fundamental electronic interactions define a static macroscopic energy landscape. On the right, the macroscopic scale focuses on the dynamic, physical movement of a magnetic field navigating that landscape. We bridge these scales by using first principles quantum mechanics to act as the material's architect, while the Landau-Lifshitz equation provides the classical laws of motion. Predictive modeling depends on our ability to transport specific quantum data directly into these classical equations of motion. The primary subject of this simulation is the magnetization vector field, denoted as M. Magnetization in a continuous material is a vector field, meaning it has both magnitude and direction at every point in space and time. This vector is physically constrained. Its magnitude remains largely fixed near the saturation point, while its direction is free to change. This poses a mechanical problem. How do we calculate the invisible, complex forces steering the direction of thousands of localized vectors simultaneously? Determining the trajectory of this field requires us to look past laboratory magnets and map the deep internal quantum architecture of the material. Computational material scientists solve this through a 5-step pipeline, establishing a rigorous path from first principles theory to dynamic evolution. Step 1 utilizes density functional theory, or DFT, to model fundamental electronic structures rather than relying on empirical fitting or guesses. This calculation provides the exact numerical parameters of the material, such as the exchange couplings, JJI, and the magnetic anisotropy, KI. These parameters function as the building blocks of the material's magnetic identity, dictating how atoms interact and which directions they prefer to point. In Step 2, we aggregate these numerical outputs to construct a unified macroscopic energy functional for the entire material. This functional describes a topographical terrain of high and low energy states. While DFT has successfully built our terrain, it remains a static map. We still need a mathematical mechanism to initiate movement. Moving forward requires a method to translate static spatial energy into a local directional driving force. This is Step 3. Calculating the local effective field. The effective field is defined as the functional derivative of the system's energy with respect to its magnetization. Physically, it is a local vector pointing in the direction that most strongly lowers the magnetic energy, illustrated here by the blue arrow pointing down the curve. The effective field accounts for external magnets, but it is dominated by internal quantum exchange and anisotropy forces pushing on that specific local spot. By identifying the steepest path down the energy well, the effective field provides the mechanical push needed to pass the baton from quantum architecture to classical motion. In Step 4, the effective field is inserted into the classical Landau-Lifshitz equation. This color-coded formula reveals a structure built from two distinct parts, rotation and relaxation. The first half is the precession term. Its vector cross product generates a torque that is perpendicular to both the magnetization and the effective field. This forces the magnetization vector to rotate around the effective field in a flat, energy-conserving orbit without changing its length. Real materials dissipate energy, which is represented by the second half of the equation, the damping term. Damping adds a vector component directed toward alignment, causing the magnetization to break its perfect orbit and move in a tightening spiral toward the lowest energy state. Modern micromagnetic software often utilizes a mathematically equivalent variation known as the Landau-Lifshitz Gilbert form. The equation perfectly models the paradox of magnetization dynamics as a tug-of-war between orbiting forever and spiraling to rest. We can ground this abstract pipeline in a real-world example, exchange-driven spin alignment between two neighboring magnetic moments. If spin 1 is misaligned with spin 2, it carries a positive exchange energy derived from our first principles calculations. Spin 1 treats the orientation of spin 2 as its local effective field. Consequently, spin 1 precesses around spin 2, and via damping, gradually spirals into parallel alignment to minimize the system's energy. This demonstrates that a microscopic quantum constant calculated by DFT directly manifests as a measurable, classical dynamic torque. It is often intuitively assumed that a magnetic vector simply snaps straight to align with an applied field, but physics proves otherwise. Magnetization must always precess first. It relies entirely on damping to spiral into a lower energy orientation. While first principles DFT provides the static map of the material, only the Landau-Lifshitz equation can drive the journey across it. The effective field driving the motion is heavily influenced by internal quantum physics alongside laboratory magnets. Successful computational models and device engineering depend on separating this static energy landscape from the dynamic motion. Predictive magnetism is built on this triad: quantum first principles, the effective field, and Landau-Lifshitz dynamics. This framework is what allows scientists to move from theoretical physics into physical application. It directly informs the engineering of next-generation technologies, from high-density magnetic storage to spintronic sensors. Modeling precession and damping enables the design of ultra-fast domain wall motion and spin-torque memory. Without the architect providing the initial parameters, the journey of the magnetization cannot be accurately simulated. Mastering the Landau-Lifshitz equation and its quantum foundations allows engineers to translate invisible atomic behavior into reliable magnetic devices.